Hello and welcome to another chapter and another first lecture of that chapter. If you've been following this lecture series, you first of all know a bit about this book, what to expect, and you know that I've mentioned momentum many times in the previous lectures. Well, we're finally there. We're finally introducing momentum. Perhaps the reason I mentioned it so many times was because it's such a fundamental idea and we just hadn't got to it yet. We had to cover, of course, motion, velocities, accelerations, and all of that. We had to cover forces, of course. We couldn't really move on. We covered gravity, which could have waited, but is so fundamental to an understanding and gets the definition of a fundamental force out of the way. And then we talked about our first amazing accounting tool because we talked about energy and the conservation of energy. If you recall when I talked about energy, I said that energy isn't new physics. It's not fundamental laws in the way that Newton's laws of motion are. All it tells us is that energy is conserved. The only law is the conservation of it. So in a sense, we only care about energy because it's conserved. Well, it's still incredibly useful. All right? And we talked about how it's a more modern development, a more modern way of thinking about physics, which of course makes us wonder what's in store 150 years from now. How will they fundamentally think about physics and approach analytical problem solving using mathematics to solve problems in a whole different way that we didn't even anticipate? Because I guarantee you that people in Newton's time never anticipated the way that we solve physics problems today. And I'm not just talking about computers, I mean even solving them by hand. All that aside, why do I bring all this up? Well, because momentum is exactly like energy. Wait, no, not really at all. Energy is measured in joules. Momentum is measured in, well, Newton seconds or kilogram meters per second. So, no, it's not at all like that. Why did I say that? Because it's conserved, okay? So that actually is a big similarity in terms of how momentum and energy are used in problem solving. And not just, the problems that are assigned in homework, but really just thinking about the world, conceptualizing things, building models, whether those are computational or conceptual or analytical. That's how we solve problems. So, momentum is a conserved quantity, okay? Now, I'm kind of jumping ahead by telling you that, right? Giving away one of the big reveals of the chapter. But we saw a conserved quantity already. We saw that energy was conserved. So I think it's so key to recognize that that's what momentum is all about. Now, momentum is interesting. In fact, I find it, and this could just be me, I find it less intuitive than energy. For some reason, the concept of energy, even the interesting equations, maybe strange equations, but somehow very easy to get kind of stuck in your brain, like the formula, the equation for kinetic energy, 1/2 mv squared, 1/2 times mass times the velocity of that thing that has mass squared, 1/2 mv squared, right? That's just such an iconic formula for me. And momentum, I don't feel like it has that. Momentum is mass times velocity. Maybe just because it's such a simple concept, just mass times velocity, that it almost belies on the usefulness of it. It seems like at least again, this is me, that I'm waiting for something more. But that's all it is. Momentum is just mass multiplied by velocity. It's the product of mass and velocity. Okay? So if something's moving, it has momentum, okay? Because it has velocity. If something's not moving, if its velocity is 0, okay, which would be the same as its speed being 0, well, it doesn't have momentum. So objects at rest have no momentum, okay? Objects in motion have momentum. Also, since mass is involved, that implies that something needs to have mass to have momentum. Turns out that the one thing we know that doesn't have mass, which is photons, particles of light, actually still have momentum despite not having mass. So, wow, that complicates things. But that's relativistic momentum and totally not what we're talking about here. It's great to go there eventually, but here we're talking about classical momentum, okay? So, let's take a look at our sections. In this video, I want to cover sections 7.1, right, because we're in chapter 7, which is momentum and impulse, some definitions. I haven't talked about impulse yet, but it's an important definition, okay? And then the law of conservation of momentum, okay? So let's take a look at our slides. So this introductory slide here isn't actually introducing collisions. If you see collisions aren't covered until the next video or a section later in the chapter, collisions won't be covered until 7.4. So why start with collisions? Because that's one of the things that we really can use momentum for, is studying particular types of phenomenon, particular types of situations that lend themselves to tracking momentum instead of using a purely Newton's law approach. Okay? I'll get back to that. I actually said something very similar for energy, so hopefully we can quickly make that connection. But let's look through this slide. So, how can we describe the change in velocities of colliding football players or balls colliding with bats, right? How do we solve for that system? How do we, have a predictive model that says, these two things are going to hit together, and this is how fast they're both going to be going after the collision? Maybe because they have different masses, or they came in with different initial speeds, right? How do we anticipate what will happen? Because I guarantee you, we know how to do that, right? That's built into so many systems. People, there's so many kind of way you hear about people knowing how something's going to work out, right? Up to a certain amount of randomness in the real world. But think about billiard balls, right? There's certain shots where the result is very expected for an expert level player, right? How do they know that, right? Because of momentum. All right, that's the best way of thinking about a collision of anything, especially billiard balls, or maybe billiard balls included. Here's another way, another kind of open question of why we care about momentum, okay? How does a strong force applied for a very short time affect the motion, right? So if something, is applied for just like a tiny fraction of a second, a millisecond, right? A nanosecond, how do you quantify that? How do you calculate it? How do you deal with, the resulting acceleration? What does that mean, right? Because you have such a small segment of time. Can you actually make a meaningful measurement? Because aren't you limited however you're making your measurements? Think, what are the great basic tools with analyzing motion is high-speed cameras, especially because they're incredible availability in the modern world. So could you do that with really high-speed collisions? No. But turns out that the video analysis would be great if you took the momentum approach that we're leading to, okay? So can we apply Newton's laws to collisions, okay? So I'm not going to tell you no, but I'm going to say that it's impractical to do so, okay? Instead, we apply a different technique. We use momentum, okay? It's the better technique for things like collisions, okay? What exactly is momentum? Well, I told you, right? I gave that one away as well. I said that it's mass multiplied by velocity. It's P equals mv, okay? How is it different from force or energy? Well, it doesn't have the same units. So in a sort of almost flippant way, I'll be like, oh, well, it doesn't have the same units. But listen, units are super important. They certainly help me understand physics. But if you just want kind of to think about, how you would visualize momentum, I mean, you could think about something that is moving with a certain velocity, right? And has a certain mass, and then maybe compare that to objects that have more or less mass or slower or faster velocities. How then would their momentums compare, right? Consider two things moving side by side, right? Consider an apple being dropped from a hot air balloon, and then consider a bowling ball being dropped from a hot air balloon, and then consider a cow being dropped from a hot air balloon. Which one would have more momentum on impact, right? Because wouldn't they all pick up the same amount of velocity, air resistance ignored? Yeah. So the only thing that would be different would be the mass. And so, of course, the cow would have way more momentum, okay? And the cow colliding into the ground, right, is going to be a case where it's very fast, all right? A lot of release of energy. So it turns out kind of fast things also would apply to a conservation of energy approach, right? Not a coincidence there. These two, kind of conserving momentum, conserving energy. There's a lot in common, but again, different quantities, right? And they have their own key focuses, okay? Not saying they're interchangeable, okay? So what does conservation momentum mean, okay? Well, that I have not clearly defined, and we'll get that. I'll actually wait till we get to that section, because that'll be the second section, later half of this video, in a few minutes, okay? So we're gonna answer these questions within this chapter. So let's just think about a situation, everyday situation, dropping a ball that bounces, okay? So we've got the iconic bouncy ball hitting the ground, coming back up. By the way, we know it doesn't come all the way up. One of the reasons we know it doesn't come all the way up is because of energy, right? Because, clearly bouncing a ball is not a perfect mechanical system. You lose some mechanical energy. You lose it to heat, right? Well, really? Like the ball heats up? Well, not exactly. It's because sound and heat behave basically the same. It's all about kind of this random motion of trillions of individual particles. In the case of sound, air particles transmitting energy. So you could call that, a form of heat energy, or you could actually, and people do, you could call it sound energy, right? Because you drop a ball, bouncy ball, whether it's a tennis ball or a children's bouncy ball, right, like a rubber ball, it makes a good loud clunk sound when it hits the ground, right? That's indicative of energy that's lost, okay? Now there's energy lost on the way down and the way up because of a little bit of air resistance, but because it's not exactly a streamlined shape like an airplane wing or something. It's what's called a bluff body, by the way, this kind of spherical shape, okay? Not maximum drag, but fair amount of air resistance. All that aside, the energy is really lost in that impact. And that's interesting because that's what we're talking about. We're going to be focusing on momentum and the change in momentum on an impact like this, the sudden change in velocity, okay? But it turns out that it ties so nicely in back with energy, because we could then, say there's a certain amount of mechanical energy before, right, that we could just quantify as, say, the gravitational potential energy that the person, has when they open their hand and let the ball fall. We know that that energy is more or less going to completely convert to kinetic energy on the way down. Obviously, I still have energy on my mind from the previous chapter, so, very little loss of mechanical energy. But then I said there will always be a significant loss here. So if you just track the kinetic energy right before impact to the kinetic energy right after impact, you would have very different speeds, right? Just looking at the magnitude of the velocity. Obviously, one would point down, the other would point up, but that notwithstanding, there would be a big drop. You would lose a lot of kinetic energy, right? Because there's a sudden loss of energy. The very fact that the way the ball bounces is momentarily stores a lot of that, what was initially gravitational kinetic energy, then became energy of motion kinetic energy. Well, it stores it for a split second in its own elastic potential energy, because it compresses, right? If you had a fast enough camera, you can actually see it, especially a tennis ball, right? You maybe have seen videos like this. You can actually see them get deformed, like significantly become like ellipsoidal instead of spherical. Okay. So then let's read the bullet points, because I think it clarifies something I'm kind of hinting at a lot, this idea of how momentum is well suited to certain situations, things that happen fast, okay? This textbook is called The Physics of Everyday Phenomenon. This chapter should be the physics of quick everyday phenomenon, okay? Still everyday, because we're not talking, like atomic fast or something, or nuclear fast, or even, chemical fast, right? But this is, in terms of everyday phenomenon, this is fast. So, ball reaches the floor, its velocity quickly changes direction, all right? It goes from one way to completely the other way, 180 degree change, okay? So there must be a strong force exerted on the ball, all right, for a very short time, right? So in this case, split second, that force is exerted. This force provides an upward acceleration necessary to change the direction of the ball's velocity. So, that's good to point out, because if this whole time you've been, screaming at your screen and saying like, this is, why are we talking about this? We already saw this back in the chapter when we talked about Newton's, second law. We have a force, we have an acceleration. Why not just give us the force? Well, the force acts for a very short time, and it also essentially acts like a big spike. So if we go over here, I'm gonna catch up on the same slide, okay? So, and I had it smaller for a number of reasons, but now, anyway, so what I want to just point out is, if we were to look at this, right? If we were to look at a little graph that'll squeeze in down here underneath our person's feet, that just showed force, okay? And this is the force applied from the ground, all right? The force applied from the ground on the ball. That's the only force we care about, right? And then we had time. Well, and when we started the time here, we said, hey, this is time equals 0, right? And then there's some, certain time of free fall. So after a certain amount of time, we get down to this point, which we'll just call T1, right? And we know how much time that would take if air resistance is negligible, or reasonably it would be, right? As I said, really, that's fine to assume. It's just, don't assume energy isn't lost in this collision, because you can actually quantify exactly how much is lost, because the floor is essentially immovable. But I'm getting ahead of myself. Here, though, what we do care about is that we know there's a certain amount of time, okay? But then, do we know how much time the force is applied, that really quick force that changes the direction of the ball? No, because it would look really rough. We'd essentially have this spike, right? So let me put it right at T1. It wouldn't have like a well-defined delta T. It wouldn't be like the force from the floor, started, a little bit before T1, kind of went up and then went right back down, right? That is not what the force from the floor is going to look like. No way, okay? Instead, it's going to be this incredibly steep spike, right? It's going to have some curvature to it, right? Because it's it's got a shape. So then, how would you actually meaningfully quantify that? Because the difference between, saying that, this slope right here is linear and it's more like a spike like this, versus it's like two parabolas that meet at a point. Those are going to make very different predictions, because it is so steep, and you're trying to get so little data to actually actually quantify this area. Because what is this area right here, right? What does the area under the curve represent? Well, it's force multiplied by time. Okay. Well, the force multiplied by time is precisely the change in momentum, okay? So this very difficult to practically calculate area under this, ill-defined little spike, we can actually well calculate using the concept of momentum, okay? Because we don't have to actually try to figure out that area. Instead, we just use a law. We just rewrite Newton's second law, right? And that's a workhorse of a law, right? So let's go through this, okay? I think I've laid the groundwork enough. Let's move through these steps, okay? So force, like these, are difficult to analyze, okay? I've definitely stressed that point, right? Strong forces that act for a very short time are just not good candidates for calculating acceleration, okay? The forces may change rapidly, as I talked about, that difficult to analyze curvature, all right? It will help to write Newton's second law in terms of the total change in velocity over time instead of acceleration, okay? Acceleration, impractical to calculate here. We're going in a different direction. We're trying a different strategy, all right? And in that process, we're actually gonna define momentum separately, okay? Which is so interesting because it's like we're rewriting Newton's second law in terms of momentum, the very thing that I was stressing we care about because it's conserved. So that's actually a remarkable use of Newton's second law, that it can be so directly applied to momentum, right? Because it can't be directly applied to energy in the same way, okay? So let's go to the next one here. So a little bit about the steps of it, okay? Because again, Newton's second law, I'm assuming you know it fairly well, F equals ma, right over here, okay? So we're just going to multiply both sides of Newton's second law by the time interval over which the force acts, okay? So we've rewritten A by its definition, because acceleration, after all, is meters per second, it's the change in velocity per time, okay? That's all we've done. The thing in parentheses is the acceleration, okay? Delta V, change in velocity, over delta T, divided by delta T is change in time, okay? All right, just may want to make sure we're clear on that. So all we're doing is what's called rearranging the equation, which is a common thing when you do these types of physical science derivations, okay? So we multiply both sides of the equation by delta T, okay? So where we're at right here is we're at the next step where we have exactly, let's go over here actually, we've got to this step right here, okay? And we got there by multiplying, as I said, both sides of the equation by delta T. So what I mean by that is this is one side of the equation, the far left side, and then the far right side is the other side of the equation. This doesn't count. That was just an intermediate step. So we'll multiply this side by delta T as well. Look how that would affect both the left-hand side, where the force term is, and the right-hand side. Well, over here, it's just going to make a new expression, force multiplied by change in time, okay? But over here, the delta T's will cancel. So all we're going to have left on the right-hand side is m times delta V. Okay. So this is cool because this rewriting of Newton's second law, which is often called Newton's second law in momentum form, specifically in translational momentum form, because it turns out there's another kind of momentum that applies to rotational systems called angular momentum. We'll talk about it really briefly in the next chapter where we go through all the angular topics all at once. But that's neat that we've done that. But the two terms I'm referring to are impulse and momentum itself, right? We're seeing it all officially in equation form right here. Okay, what do I mean by that? Well, the left side of the equation, the part that's just the product of net force, I kept saying force, but it's net force, because just like when we use the work energy law, it's net work, right? With Newton's second law, it is important to remember it's not just one force, it's the total sum of forces acting on whatever object you're paying attention to, right? Maybe the ball, right? So it's net force times delta T. That whole thing, that product, is called impulse, okay? So it's kind of like we defined work as the product of force and displacement. Here we're defining something called impulse, which is the product of force and time, okay? Or elapsed time. And if we'll go back over here super fast, I'll point out that we should have a letter for it. A lot of textbooks actually kind of hesitate to introduce an extra letter. I don't know why. I think we're used to seeing a letter for every named variable, and there is one that is widely used, and it's J, uppercase J, by the way. So we have then that J is impulse by definition. Okay, that's what the letter is for impulse, and J is equal to F net times delta T. Okay, so the product of net force and elapsed time. Okay, that's what is impulse. Okay, why are we introducing a whole nother thing if we're already talking about momentum? Because impulse and momentum are the same. They actually have the same units. Okay, which I always think of as a odd exception, because I can't think of any other example in physics where two quantities that have the same units that are both translational, so neither one's applying to like a different kind of coordinate system, so they're both applying to the same coordinate system, have their own names, right? It'd be like if we gave a name to change in velocity. Because we gave a name to change in velocity over change in time, that's acceleration. But what if we actually named just the change in velocity itself, right? We don't have a name for that, it's just called change in velocity. But impulse is, by definition, the change in momentum, or it's defined to be equivalent to it. But what's interesting is it's also defined as force multiplied by time. So force applied over some time, okay? Sometimes they start to say force over time, but if you just say that, then you're saying force divided by time. But if you say a force applied over some time, then you're talking about the situation. It's probably better just to say force multiplied by time, right? But let's look at this real fast, because this next bullet point, or next paragraph, talks more about impulse. So impulse is how a force changes the motion of an object, or rather related impulse. How a force changes the motion of an object depends on both the size of the force and how long the force acts, okay? So this product of force and time, impulse, okay, it can be big if you have a big force over a short time, or it can be big because you have a small force that you pushed really gradually. Although, honestly, if you had a small force that you pushed over a long time, so gradually applied, then you'd probably be in a situation where you might as well just go back to using acceleration. Because don't get me wrong, there are plenty of situations where using Newton's second law, or the equations that apply to uniform acceleration, are completely the best way to go, like any free fall situation or any projectile situation, right? Because gravity is a pretty strong pull, but it's gradual, and often the time we spend exposed to it is milliseconds, right, or minutes even. So that's great for using the approach of acceleration, right? But that's not what we're talking about here. So the right side of the equation, right? So going back to the equation that I've been keep drawing your attention to, the part that is just m times delta v, that is, by definition, change in the momentum. Because momentum, which has its own letter, uppercase P, okay, that's what we use for momentum. I know it doesn't match the first letter of the word, but uppercase P is momentum, okay, is equal to, right, defined as mass times velocity. Every object that's in motion has a momentum, okay? That's what momentum is. It's just the product of mass and velocity. And if we're going to look at its units real fast, that's a good time to do so, all right? We see then, right, so momentum, by definition, represented by the variable uppercase P, has units, put those in parentheses to make it clear that we're talking about units, not variables. Well, it'll be the kilogram for the variable m, and then for the variable v, right, here's shown as an uppercase V, which is not typical. We usually use uppercase V for volume, but it's just drawing attention to this is the big thing you care about. This is the thing that's going to change, right? Because then you're rarely going to have a case where you care about changing momentum. There's kind of one special case that we talk about very conceptually. Remember, this is after all a conceptual physics class with just a little hint of math, right? Right? We just spend most idea of yes, presenting the equations, but more about their proportionalities, more about understanding them like a balance. But all that aside, when we look at this equation, m is usually not going to change, but it does for one particular case that we touch on. That's called the rocket, right? Because the rocket is a case where the rocket's using up fuel, a significant amount, and that fuel was a big part of its original mass. So there's a big change in its mass over time, okay? But usually doesn't change, right? Certainly not for a collision of a ball, right? The ball stays intact, it's the same mass, right? Before and after it hits the floor, right? So then I was saying the units of velocity are meters per second. So then the overall units of momentum are kilogram meters per second, okay? That's fine, you can write it that way, but there actually is a more intuitive way to write it, which ties it in nicely with impulse, because if you look at this, kilogram meters per second is an awful lot like a Newton, because a Newton, by definition, right, I'm not saying that momentum is a Newton, I'm just pointing out what a Newton is. A Newton is defined by Newton's second law, right? The Apollonius Newton. Well, when you look at Newton's second law, it's mass times acceleration, so it's kilograms times, right, kind of like this, right? But instead of velocity, it's acceleration. Well, what's acceleration? Meters per second squared, right? Because meters per second. Well, then the only difference between this, expression for momentum and the already, hopefully well-known expression for, force, the Newton, is just the difference of having an extra second in the denominator. So that means that momentum, right, the units of momentum, the kilogram meters per second, can be correctly expressed as the Newton second. Because if you multiply a Newton by a second, think what would happen, right? You'd cancel out one of the seconds, one of them, in the denominator, leaving only one behind, making it look exactly like you want it to. So a Newton second is a kilogram meter per second, and is the units, or they are the units of momentum. And I said it draws attention back to the whole fact that change in momentum and impulse are equivalent, and this whole idea that impulse and momentum have the same darn units, because we use these units for momentum, Newton seconds, and then look at the definition of impulse, it's force times time. Well, that of course is also Newton seconds, as it should be, okay? So again, what's the difference then between momentum and impulse? It's just how you come about it, right? If you're told the average force, right, the average net force, and you're told how long it applies, right? Maybe you know that information from some estimate, I said that's the harder thing to know, but maybe you know that, right? Well, then from that information, then you could get the change in momentum, right? Or maybe more likely, you know the velocity before and after something, right? Going back to the ball drop, right? You know V1 and V2, right? Immediately before and after the collision, okay? Here they're kind of showing like, pretty far before and after the collision, but again, assume there's no air resistance. But what we have then is we know those two velocities. If you know those two velocities, right? Well, then you've got your delta V, right? Because it'd be V2 minus V1. Okay, that's all delta V is. V2 minus V1. Okay, V final minus V initial. Okay, but here we're using 2 and 1. Okay, so you know that. You know the mass of the ball. Check out what you know then. You know the actual impulse value. You know the change in momentum. So that's cool, because then if you know, say, like the net force, right? Then you can calculate the time it was applied. Or maybe more likely, just based on maybe some, the frame, right before you, like going back to video analysis, but you see this, high-speed camera, you see the ball right before it hits the ground, and you see it right after it's obviously not in contact with the ground anymore. So you get a good estimate of delta T, right? That's more likely what you'd actually measure. Now you actually have a way of calculating force, something that'd be very hard to measure directly. Okay, so another use of momentum. Now comparing momentum, I mentioned this before, and this was the figure I was thinking of, like visualizing it, or rather comparing momentum between things is a good way of visualizing it, a good way of making sense of what it really is. So here we have a case, right? It's like I said, it's the dropping the cow out of the hot air balloon, dropping the ping pong ball out of the hot air balloon. Well, that one's hard not to imagine having air resistance. Okay, so let's say dropping the cow versus dropping the bowling ball. Which one has more momentum when it hits the ground? Clearly the cow, because they both have the same velocity. But could you have an airborne cow and an airborne bowling ball have the same momentum? Sure, right? Yeah, the cow is a lot more massive, but what if it wasn't moving as fast? Right? So what if you had a cow moving at 2 meters per second, right? And you had a bowling ball moving at 75 meters per second. Well, that significantly extra velocity could make up for it, right? Now what's interesting is that it's just directly a product. It's a linear relationship. It's just mass times velocity. So if you know the bowling ball is 1/100th the mass of the cow, then you would literally have to have the bowling ball go 100 times faster for the two objects to have equal momentum. Okay? So that's the idea, and here it's showing with a bowling ball and a tennis ball, right? No cow. Okay, so we've said this, but it's good to call extra attention to it. So this equivalence between impulse and momentum is the impulse-momentum principle. Okay, it's actually a similar principle to the work kinetic energy principle, right? It's like we define these separate things. They're not really different, right? They have the same units, but we have we could calculate them practically in different ways. So yeah, we define them individually, but we remember that they are equivalent to each other. So we might go back and forth. So here's a case where, like I was saying, you might know some aspects of impulse, like the change in time, but not the force, and then you might know everything about the change in momentum, and then you can calculate your one unknown. Because really, this equation has 4 things you could potentially not know, right? So if we think about this real fast, and I'll kind of write right over it the 4 things, okay? So basically the 4 things that we don't know about this equation, or that we could solve for algebraically, right? On the impulse side would be the force, right? I want to write this in a permanent pin. So F net, okay, that's one of the things we could solve for. The other thing would be delta T, okay? And you would solve for that not as two separate values, it's just a single thing, right? Because it really is, right? It's just some amount of time that passed, okay? So think of that as a single variable. And then on the right-hand side, the delta P here, okay? Remember, P is our new letter that represents momentum, but when we expand it out, what's inside of that P, an M and a V, right? So we just have an M, and then instead of the delta V, here you kind of have two more things, so I guess there's a sum of 5, I lied, because you think about it, really here you have V final minus V initial. And here you really could, again, often you might solve for delta V collectively, right? So just like I was saying, you always would for delta T, right? You just, the difference in the velocity was 5 meters per second, because before it hit the ground, it was traveling at 3 meters per second downwards. After it hit the ground, it was traveling at 2 meters per second upwards, okay? So the difference is 5, right? Not 1, because you might think 3 minus 2 is 1. Well, how'd you get 5? Because it was negative 3, okay? Think like a number line here, right? So we had negative 3 as the initial velocity, right? So V initial, okay? Negative 3 meters per second. Over here, we'd have 0, right? Continuing on the number line. And then over here, we'd have positive 2 meters per second. What's the distance between those, okay? Right, and this is V final, right? Well, the delta V here is 5 meters per second, okay? So yeah, you might just solve for that value, or maybe be given that value, right? But other times you might know either V initial or V final and just have to find the other one. In that case, you would know everything else here. You know the net force, you know the change in time, or maybe you don't care, right? Because maybe maybe you're just given the impulse value, okay? So just to call attention to the things that you might be actually applying this equation to. Okay? So, right, expanding on a little bit. So here we have nice pictures, right? We've got the ball coming down. It has some initial momentum, okay? See how they're the whole momentum here, right? Because that's what we care about, right? A lot of times I'll draw the picture with the velocity because as I pointed out, the mass isn't changing. I can bring the mass in later in my calculations, but it's also good to call attention to that is, after all, momentum that we're tracking, that we are tracking. Okay, so then there is some change in momentum. Okay, that change in momentum happens during a very short time where an impulse is applied. Okay, by the time that's all over, there's a probably much greater time for it to gain just this amount of extra airborne height. But again, the airborne height we're ignoring because it takes place in an approximate vacuum, right, or negligible air resistance. But what we do care about is that P final, right? So the whole thing is that the P initial went to the P final, and it happened in some practically unmeasurable small amount of time where a impulse was applied, okay? So what do we got then, all right? So we know in this case that it was traveling at negative mv on the way down, and it was traveling at positive mv on the way up. How is that different from the example I just did, right? Well, in my example, I had to go at negative 3 and up on 2. Why did I do that? Well, because I keep talking about how realistically it loses a lot of energy. That's on my mind because when I do labs with my students, I always see this happen, right? There's a big measurable loss of energy, and even the best bouncy ball, right? Even the best tennis ball, even the best ping pong ball. There's just no way. It's just the process inherently involves a lot of energy loss. You just can't have a collision like that with an unmovable floor, right? Total energy loss, yeah, and significant. So you're never going to see a case where it was negative. It was negative mv on the way down, positive mv on the way up. You can't preserve the momentum that well. All right, so regardless, that's what's happening here. Now, is that totally impossible? Because I just said, it can't happen. Well, I mean, no, there could just be something else that is in the system that is kind of outside of what we're paying attention to. Because we just care about the change in momentum of the ball. That's all we're trying to quantify. Maybe it was able to, completely seemingly recover its momentum, but going in the other direction without any loss of momentum, therefore without any loss of energy. Because by the way, if you lose momentum, you lose energy. How do I know that? Because the only way that this ball would lose momentum is lose velocity. It's not going to lose mass, right? If it loses velocity, what will happen to its kinetic energy? Kinetic energy is 1/2 mv squared. V goes down, so does kinetic energy. So losing momentum is also losing kinetic energy every time, okay? Right, because even if you lost mass, that's also in the kinetic energy term. So every time. Right? Now, here's the thing though. Now, Could this, kind of retention, no loss of momentum, come from somewhere? Sure. It could come from the fact that maybe there was an extra little kick on the floor, right? It was, a floor with like already some stored elastic energy in it, right? So there's certainly situations where it could happen. Okay. All right. So then let's finish with this few slides to cover conservation of energy, and then we'll leave off on recoil. That will be covered in the next video. If you're wondering what the heck's recoil, that's like shooting a cannon or like a musket or something, right? Honestly, a gun as well, right? And then what's going to happen is it's going to have a kickback, right? Called a kickback, also called a recoil. That's absolutely conservation of momentum. It's just a textbook example of conservation of momentum, all right? And as are collisions, especially things like billiard balls, or in this case, people, right? When people crash together, we have an intuition of what happens, right? If they had exactly equal mass, right? If these two football players have exactly equal mass and they came in with exactly equal velocity, then they came in with exactly equal momentum, okay? But equal in magnitude. Because is momentum a vector? Sure is, right? Look right here, right? Momentum is a vector, right? It has direction. It has the same direction as velocity. So if you have two equal magnitude momentums that are coming together and colliding, then you could end up with a case where what happens? I bet you know, right? They would just both come to rest, right? Now it's an idealized case, right? But under just the right circumstances, maybe it happens, right? They just happen to have maybe one player was more massive than the other, but then that player was moving slightly slower than the other. So they came together with exactly identical momentum in a perfectly straight line, and they just stopped, right? So that's actually what conservation of momentum tells us should happen. So it's matching our intuition, okay? So does Newton's third law still hold in this situation? Okay, well, absolutely, okay? And students and myself, often sometimes we'll be musing, or sometimes all students kind of say, well, what the heck? We should solve this with Newton's third law. Why are we using momentum? And you actually sometimes can totally choose. This is a case where sometimes there isn't a clearly better way of doing it. Because Newton's third law, we get the force pair, we can then solve for things like the final velocity afterwards, right? Because we can just consider a situation where we can ignore acceleration and just go straight to the forces, okay? All right, so if the net external force acting on the system, okay, of objects is 0, the total momentum of the system is conserved. Okay, this was the thing I was holding out for, because there was a question early on. I basically answered all the other ones, but in a sense that I knew we'd have to revisit them. But I never answered it, what actually means, or what has to be true for momentum to be conserved. Because all of the conservation laws are not universally applied, right? Like mechanical energy isn't always conserved, because mechanical energy can become other forms of energy. Now, is energy absolutely unequivocally conserved? Well, no, actually there's a broader law that says that there's an energy mass equivalence. So saying that energy is conserved, you'd be caught saying that's wrong, because you're not looking at the system in a broad enough way, because you're not considering Einstein's E equals mc squared, that mass can become energy and energy can become mass, right? That's a big idea. So why do I bring that all up? Because, right, momentum conservation, the law of momentum conservation also only applies to certain situations. Does that make it kind of like a corner case? Like, we have to be really careful to make sure that it applies to this situation? Well, not really, because it turns out that all the situations that we've been highlighting, the ones like collisions, fast collisions, explosions and recoils, essentially that's what's happening in a gun, right, or a cannon. It's a controlled explosion and there's a recoil, right? So a very fast release of energy, and also a very fast release of our objects very quickly going from zero momentum to large momentum, right? Zero velocity to high velocity, right? In the case of launching something. But what those cases have in common is that they happen quickly, right? That was why I said that we shouldn't try to solve for acceleration, right? It's too messy. But that's also why it turns out the conservation law is so well suited. So the fact that it happens fast simultaneously discourages us from using Newton's second law and encourages us to use conservation of momentum. Now, that's probably the way this field has been developed over centuries, but it's still cool, because having conservation of momentum only apply to situations where the external force is 0, okay, is perfect for things that happen fast. Right? So if you have two people crashing together really fast, two billiard balls crashing together, right? The gun exploding, right? So the gun recoil down here, right? All those things, they happen so fast that external forces like gravity, right? That's a big one, don't have time to make a difference on the outcome, right? Because once the shot, in this case, because it's like an old-fashioned shotgun or something, right? So a bunch of little pellets. Once those pellets have been, moving for a while, well, then it's completely naive to say they're still moving in a straight line, or that they even still have the original momentum, because gravity is going to cause them to arc downwards, right? Absolutely. So that is an external force. That's momentum not being conserved, right? But that's later on. So momentum is what we use for the fast, sudden effect, and then we can actually track the result of that, because one thing we can do is we can have something like launching a cannonball or launching little pellets from a shotgun or a musket, and then tracking them, finding out how far they go, what's their range as a projectile. So what's cool is that would be a two-part problem where you use conservation of momentum for the fast part, the explosion, right? Then you use Newtonian laws and uniform acceleration in the corresponding kinematic equations to deal with the slow millisecond phenomenon that follows. Okay, so two separate tools for two separate parts of an overall process. All right, so now let's go back to our players. Okay, so that's the idea. Momentum is conserved as long as there are no external forces. Okay. So the impulse on both are equal and opposite, okay? That's this special case. The changes in momentum for each are equal and opposite, okay? Yeah, everything's conserved, okay? The total change of the momentum for the two players is 0. What does that mean? Well, because they both had momentum coming in, right? They had some amount of initial momentum, right? Now, how much initial momentum did each of them individually have? Non-zero, okay? But how much momentum did the two of them collectively have as a system? Because taking the two players and saying this is a two-body system is exactly the kind of thing that physics likes to do, that physicists like to do. Okay, three-body systems we don't like so much, but two-body systems are great. Okay, because then we just use all the same tools that we would for a single-body system. Okay, we just say, okay, we got these two things, right? They now have each their own momentum vector. They're each equal in length, but opposite in direction. So if we sum them, the sum is 0. So that means that the initial momentum of the two players collectively was actually 0, even though they each individually had non-zero momentum. Which means that afterwards, when I said that intuitively we know they both just come to rest, right, entangled in each other, well, in that case, the final momentum is clearly also 0, because there's no leftover velocity. But that works, because the initial momentum was also actually 0, okay, for the two of them. So it's a cool demonstration of conservation of momentum, all right? So now let's look at a case, though, where the final result won't be 0, because although that's so neat, it doesn't, I don't think, highlight the process of solving it very well. So what we're actually going to do in the next few slides is something that the slides don't do all that often, actually work through a numerical problem, which saves me the work. So a 100 kilogram full back moving straight downfield at 5 meters per second collides with a 75 kilogram defensive back moving in the opposite direction at 4 meters per second. Okay? So we've got, so we have 100 times 5 is going to be the momentum of one of them. So I'm looking, that's obviously going to give us a 500. And then, so yeah, the bigger person is moving faster. And then the smaller person, all right, is moving slower. Yeah, so that it's really going to drive them apart, right? So this player, this one here, the one in green, is shown smaller too. It will have significantly less momentum because they're both lighter and slower, okay? So the defensive back hangs on to the fullback and the two players move together after the collision, okay? So this is, in collision terminology, this is called, and you'll see this come up here in section 4, an inelastic collision, okay? Now, we'll define that again when we get to that section, okay? That's just any collision where they stick together, all right? So what is the initial momentum of each player, okay? So let's start there, all right? So go ahead and calculate these, okay? Great practice to do so. Pause the video, right? Okay, so now I'm going to show you the results of the calculation for the individual momentum for the fullback and the defensive back, okay? So with the fullback, its momentum is mv, right? It's, I guess, his, right? Their momentum, 100 kilograms times 5 meters per second, okay? So you take that product and you get 500 kilogram meter per second, okay? Or the units I like to use, Newton seconds. Both are fine, okay? Then the momentum of the defensive back, okay? Well, I was focusing on its magnitude, thinking about, which person is going to end up getting moved more afterwards, obviously the lighter, slower person. But now not just the magnitude, but the negative is so important, okay? Just as it was for the case where everything's zeroed out, because otherwise you will not get the correct result, right? You gotta remember that momentum is a vector, and this player, right, although they have a smaller magnitude momentum, do have a negative momentum, right? Opposite direction, okay? So it's 75 kilograms, no negative there, mass is just always positive, but then multiplied by their, not speed, but velocity, which is negative 4 meters per second, right? Because velocity is the one that has direction. So then what you get for momentum is negative 300 kilogram meters per second. The negative just means that they're moving to the left. How do we know that? Well, that's the traditional direction of negative, and right is the traditional direction of positive. If we're being a little bit more careful, we actually might just draw the direction of positive x on the figure. I tend to do that, right? Some of these books don't, because they don't want to clutter up the image and make it look overly complicated, but I hope we can agree that normally the positive direction is towards the right, okay? At least, in the United States. Okay, so the total momentum of the system will just be the sum of these two values, okay? But the negative matters, okay? So we take the total momentum, sum of the momentum of the fullback, plus the sum of, it's just the sum. So the total momentum is the sum of the momentum of the fullback plus the momentum of the defensive back, okay? So 500 minus 300, 200 Newton seconds, okay? Or 200 kilogram meters per second, all right? That's the total momentum of the system, okay? And there's nothing else in this system. We certainly don't care about things like the ground, because if we included the ground in the system, well, it's, I guess, on the one hand, if we included the ground in the system, then we don't have to worry about friction, right? Because the ground otherwise might be a unignorable external force acting on both players, right? If we included it, then now it's part of the system, it's not external. That was the condition, after all, for conservation of momentum. So in some sense, you actually can make your system bigger and bigger, so it includes everything that you need to, so now you don't have to worry about any external forces, right? Because if you zoom all the way out until you have the planet, then are there any major external forces? Well, unfortunately, there actually are, because of, after all, gravity, right? The orbit around the sun. So that actually, looking at planetary motion, that'd be a really bad one for conservation of momentum, okay? That's all about momentum constantly changing. But anyway, I get off topic. The point is that we're assuming no external forces. A reasonable assumption, not for a whole, run down the football field, but for the moment of the collision, sure, okay? And here they come, right? So we're going to have them crash together, all right? Importantly, when you do this, and it's something easy to forget, is that since we are going to consider the momentum after the collision, in which there'll only be one object because they're locked together now, well, that new object has the sum of their masses, obviously, okay? So now we have a new object, the collective, fullback plus the, just forgot the term, defensive back, is 175 kilograms, okay? All right, so then what's the velocity? Well, the momentum after the fact, the total momentum, must be the same as the initial momentum, because that's what conservation told us, right? So, right, let's go, let me show you that real fast. And go over to our football player, right? We're just over here, okay? So the reason that we can confidently say this equation right here, because otherwise it might seem like we could just kind of jump to it. The reason that this is true is because, right, because this, after all, is the velocity of them after the collision, right? This would be like V, final, or V2, whatever you want to call it, right? Because they both had their own initial V1s, okay? Well, the reason that we know that this P total, right, P total, all right, equals P final equals P initial, right? Because after all, the P total, the 200 we're plugging in, that was the momentum before the collision. But that's the whole point. That value hasn't changed. That's the tool of using conservation of momentum, that we can find the momentum before something happens and know that that value is going to carry through. And that will allow us to solve for other things. In this case, the final velocity of the players, okay? All right? So afterwards, right, after the fullback holds on to the defensive back and continues to move, holding on to him, they will continue to move in the forward direction, because after all, the fullback was more massive and, just had a bigger momentum because they're more massive and they had a greater velocity. So that definitely wins out, and we move forward at a rate of 1.14 meters per second. If we had changed some of our values, what if we, made the fullback 125 kilograms instead, right? Really big. well, then we just get a slightly larger velocity here, right? So you can think about how tweaking would get the results that you may expect, okay? So the velocity is in the direction of the fullback, okay? Right? So, and again, it will always be in the direction of whichever player had even slightly more momentum, right? Or in that case, the velocity might be really small, right? Because there's no way for it to go the other way. It's either going to be completely at rest in where they're exactly equaled out, or the final result will be carrying on in whichever momentum vector in this one-dimensional case was slightly bigger. Okay? All right, so in the next video, we'll talk about more conservation of momentum because that's the way we approach recoil. So in a sense, we've laid the rules, okay? Now we're just gonna apply them to a few particular situations. Sounds like fun, right? Well, stay tuned for the next video for that much fun. I hope this video introducing momentum, impulse, and the conservation of it, and tying it in with a bunch of other ideas in classical mechanics has been both interesting and informative. Thank you so much for watching.